I think we're just going to get started. Sorry we're a little late. Hopefully everyone got some pizza that needed some. We've got chips also, drinks, but otherwise, enjoy the presentation.
Great to see such a big turnout. We're really excited to be here. So my name is Angela Wang, and with me is Dr. Tammy Chang and Jeff Day. So we are really excited, and the topic is all about radio, and that was a creation by Richie and Ryan. So that's what we'll talk about. I'll start with satellite radio communications and systems engineering and the transceivers. The next chart. So this is the flyer that Richie and Ryan came up with, and I want to really point out the tiny URL here. If you go to that link, it's associated with this event, and you can upload your own information and be in the talent acquisition database at Lockheed Martin, and it's specifically for college students. And this is the very best way if you want to explore opportunities for either internships or after you graduate. And so if you don't remember this link or anything, just email IEEE and they'll send you that link. All right, we'll start with satellite radio communications. It's just one form of radio. So I've been here for 17 years. And before that, I earned a PhD at UC Berkeley. And at Berkeley, there's an organization called WCSY, the Women in Computer Science and Engineering. And in WCSY, if you guys know Professor Belle Way, she is the Dean of the College of Engineering right here at SJSU. So Professor Belle Way is a classmate of mine. We didn't actually overlap. So her specialty is in digital logic design. And my specialty is in adaptive signal processing and equalization. So we all know what equalization is, right? Anyone with a radio, you know when you adjust the treble and the bass, right? That's a very simple form of equalization, so we all know that. And radio itself is a Latin term for radius, radial, and radiation. And we all know radiation because we all have smartphones, we all have wireless earbuds, we all have iPads, tablets, we have key fobs, garage door openers, remote control, cordless phone, Amazon Echo, Amazon Dot, Fitbit, smart iPhone. We've got radiation. We all know how to do that as a consumer. But what if, for example, like my family, you're a victim of Hurricane Katrina, and nature has just wiped out your infrastructure? What do you do? Or if, like right now, you are in Ukraine, man-made forces have wiped out your infrastructure. So what do you do? And so we're here, myself, Tammy, and Jeff, to give you an insider's view of the radio, and in particular, insider means the engineer's view. Okay, so the first part I'll talk to you about is satellite communications, which is one form of radio, and this is the work we actually presented right down the street in San Jose about a decade ago. Next chart. Okay, so for this program, here you see in the middle is, do we have a laser pointer? I don't know. So we have the three 18-meter parabolic Cassegrain dishes in Waihiwa in Pearl Harbor. And I actually spent quite a bit of time there. And then above that, here is the 8-foot-long UHF helical antennas. And if you guys came on April 19th, you would have met Kevin Griffith. He actually designed those antennas and built those antennas. So the type of orbit this is called geosynchronous equatorial orbits. And so I would like a brave volunteer to come forward and tell me, without looking at your phones, where you think this geosynchronous orbit is. So if this is the Earth, am I going to have a volunteer come up and tell me where you think geo orbit is? So this is Darren. He's an IT specialist. Put your index finger where you think it is. Geosynchronous equatorial orbit. Good, good. How far away from the Earth do you think it is? If you had to sort of go that way, put your index finger where you think. Okay, good. Any other guesses? Okay, so geosynchronous orbit is 3 Earth diameters away. So the Earth's diameter is 12,736 kilometers. So you need 3 of these. So 1, so you do it. 3. Well, go this way. So this is 1, 2, 3. It's right here, right? This is where geosynchronous equatorial orbit is. So another type of satellite is called low Earth orbit, the Elon Musk Starlink. So where do you think that is? So that's back where Darren said first. So these geo orbits are used in many applications. They have different aspects to it, but I just wanted to point out where they were. Okay, so great, thank you. Okay, so where Darren's index finger was is this satellite. And this is the human being scale. Okay, so the top here is the unfurlable mesh antenna, and the bottom are the UHF. That Jeff will talk about UHF frequencies, and then here I'll talk about this Ka frequency. So the next slide, I'm going to show you how I specified and modeled the transmitter radio on this satellite for that distance. Okay, so that was a satellite application, but what I'm going to show you applies to any digital radio. So here, before I start, this is what one of the takeaways I want you to always remember. This came out just recently, this year, okay? The Keysight says EVM, which I'll tell you about, is the heart of everything wireless, and that's really true. And so when I was younger, I was also selected to be a cover model, just like this. They put me right like this in a lab, took a picture, and then what I'm going to show you is how I wrote software-defined radio that does what's in this box long before she was born. All right, so that transmitter that I told you about, this is the digital signal that's coming out of it, and this red line is the error from what it should be, and you want that to be small. And the metric is this error vector magnitude. So without going into all the math, this is the error vector magnitude on the constellation, and all you have to remember is EVM squared is 1 over inversely proportional to the signal to distortion ratio. So the larger the EVM, the smaller the signal to distortion ratio, which is bad. All right, so this is work we did on EVM in 2006 that I presented in Washington, D.C. So who knows who Tom Brokaw is? Some people? Okay. I was the guest speaker. I was the speaker right after Tom Brokaw in Washington, D.C. Next chart. So this is the model of the transmitter. Everything here, this part is the transmitter here. So very quickly, the way you model it, that I modeled for Washington, D.C. is the coding, which is the forward error correction, not shown here. Then the end coding is how you go from bits and end tuples to a symbol. For example, if you've taken Professor Morales' class, then you know you can get BPSK, QAM, that's this encoding. Then you upsample and you perform the Nyquist root raised cosine on the transmit side, and then the digital to analog converter. So each one of these components has a distortion that you would model as the systems engineer after you perform the mission analysis. Then is the phase noise from the up conversion, and then the TWTA, which is an amplifier that will also produce distortion and compression, and then finally the output filter for spectral containment. That will also have ripple and group delay distortions that you would model. So everything here I showed you on the satellite is on this left box. I'm gonna skip all this for now, and then on the right-hand side is the receiver, okay? So next chart. So this is the receiver. So where Darren had his finger, then this is in Hawaii. And I actually spent 4 months in Hawaii in a double wide trailer right here on the bottom of the picture underneath these antennas. And modeled, before these were built, modeled the receiver. So, okay, next chart. So that's the satellite application, communication systems engineering. This is called the systems engineering V. So everything I told you was on this left side, the requirements and the modeling, right here. And then after that, a large team implements, right? So we have the unit engineers, the specialists, the technicians, the assembly people, the QA. Tremendous amount of work goes into building that satellite in that picture that I showed you. Then when you come out of the V on the right-hand side, then when people like me, the systems engineer, comes back in, then we check the results to say, did you build that satellite the way that I told you to? Does it perform the way I expect you to? So that's the next chart. So then in 2009, I presented that other side of the V in Boston. Next chart. So this is on the receiver side. This is after the signal comes out of that satellite picture that I showed you. What do you do with it? You have a series of functions on the DMOD for your radio, and then you come back out here and measure your resulting EVM. Okay, next chart. So on the left-hand side is what happens if you had 0 distortions. Those guys built the satellite perfectly for me, and everything is good on the left. In the middle is what they came out with, and we all looked at that, and I would say for a multi-billion-dollar program, there was extreme panic across a very large organization, because this was not what I told them to build, and there was a big problem. So then what happened is, well, then because I told you I know equalization, I used equalization to remove the portion that didn't actually belong to the satellite. It was just the test equipment. So then after I did the equalization, it came out to be like this, which is exactly what I specified to them 3 years before they built it. So the summary here is that this large bandwidth for military was not met by commercial test equipment at the time. That's why we had to do everything by hand, because there just simply wasn't a solution. Okay, next chart. Okay, so that's it.
Okay. So I guess I think just do right here up. Okay. Yeah. So hi everyone. I think first of all, Angela didn't she went through very quickly, but what she's done is very impressive. I'm a relatively new employee to Lockheed, and have been looking at MUOS, which is the satellite system that she built, and I frequently come across documents that she has signed off on. So there's quite a legacy there. I guess my background is electromagnetics and antennas. I did a little bit of wireless systems in the past as well. I mentioned I'm new to Lockheed, 4 months there. Prior to that, I was at Lawrence Livermore National Lab for a little over 3 years, and then before that, I was a grad student finishing my PhD. So what I understood of the wish list of what we could talk about today, I think antenna design was in there. I don't know who wrote that wish list. Is that
Richie.
Okay, is he here?
Richie's here.
Okay, so I saw antenna design, I saw S parameters, so that's what Angela asked me to focus a little bit on. And so I thought I would do 3 different projects that I've worked on over the years. And they're all, the first one's a little smaller, the last one took 3 years to some percentage. not working 100% on. But my goal is to get you, give you a taste of what someone like me might be doing on antennas and EM from a research perspective, and why I think it's exciting, and maybe you will think it's exciting too. So the first one on the left is a graduate student project I worked on. That's a dual band antenna for athlete concussion monitoring. So I'll talk about all of these in more detail. The middle one is a stretchable antenna design for biomedical wireless power transfer applications. That was part of my PhD dissertation. And then the last one is something I worked on over the past couple of years, how to do diagnostics for advanced manufacturing systems. So in this case, it was liquid metal jetting, which I'll also talk a little bit more about. But how can we use electromagnetics to actually act as a diagnostic for it? Okay, so that's kind of, oh, and this is what I worked on, I think I mentioned already, for the past couple of years. Next slide. Right there. Right there. Yeah. Okay, so I actually don't know where things are at right now, but if you follow football, you probably know that concussion has been a major consideration over the past couple of years. There are athletes that, years down the line don't want their sons to do football anymore because of the impacts of concussion. And so in 2012, there were a couple of, I don't actually know where it got to, but I know that this is a continued research effort. Lawrence Livermore is also looking at it. They're doing modeling of the brain and the concussion effects. But at Stanford, there were some professors who are interested in basically adding sensors into the helmet and the mouth guard to look at how different impacts during football activity would result in concussion or non-concussion. And so the question that we had for this course was, well, can we, you can put the sensors in, but is there a way you can offload the data while the testing is actually happening, right? And the second piece was, can you also power it? Because you're putting just thinking about the mouth guard part, you're putting a really small board in, there's how can you maintain data during for a longer period of time while an athlete's doing something? And so we basically had this question posed, which was, can you put these two types of antennas, or two antennas that operate at these very disparate frequencies, right? This is 2 orders of magnitude difference. Can you put it on this tiny circuit board and not have them interfere with each other and still perform very well? So next slide. So to be perfectly honest, I don't remember the specifics of this design, and I had to look at the paper again this morning. But the short of it is, what we did was, so there's 2 ways you can do it, right? You can put, when you design antennas, you can put just put them as far apart as possible. That's your way to reduce coupling to each other, right? But this design, what was interesting about it that we came up with was, what if you make them part of the same antenna? Which is not that unusual if you're working in 2 frequency bands that are very close together. But if they're very far apart, it does require some creativity. And so what we did was, what's being shown here, first of all, is, can you guys, what is this parameter? Amps per meter? Does anyone learn that? Amps is current. Amps per meter is surface current. So it's a common way we look at antenna design. And so what's being shown here is areas where there's more current on, all of this is metal, right? And so you see the front side, back side, there's these 2 small circles, those are vias, but this is one big loop, basically, with a little thing sticking out of it, which is that thing there. And so, without going into the details, what is being shown here is that you can, with one antenna, that's all one antenna. If you do the design creatively, you can have your currents actually on the front and back help each other. Rather than, for example, if you have on the front, your current's going this way, on the back, your current's going this way. From a distance, what do you see? No net current, right? But if both directions are the same, front and back, actually helping each other. So that was kind of the basic idea of the design. The specifics I don't actually remember that much. And then what we see here on the bottom is, the left is the Bluetooth performance, so that's the return loss. This one, all the way at the bottom, much lower frequency, that's the return loss for the NFC antenna. And then this is showing the coupling between the 2. right? It's fairly low across the whole spectrum. Okay, so that's the first project. We go on to the second one. Okay, so another thing that people have looked at is how many of you are familiar with implant devices, like cardiac implants-ish? You know what the size of those usually are? Okay, I guess they've gotten smaller. But in like 2013, 2015 timeframe, they had like, some of them were like this big, right? Or maybe this big. And a big chunk of that size was, do you know what that was? Taken up by? The battery, right? So then you put this large thing into the body, and then when the battery runs out, you have to like
Oh no.
cut open again and replace, right? And so there was a lab at Stanford where they were interested in, well, what if you take the power part out? So you leave the device inside, you still have like a little coil to capture power or capture the waves that you're sending in, but you move everything else outside. So wireless power transfer into the human body. They did this optimization to say, okay, if I want to optimize the power transfer and the focusing to just a few centimeters into the body, what frequency range should I, or what frequency should I use? And at least for them, they came up with around 2 gigahertz, a little under. And then they also came up with this design for how you can do the focusing on the outside with an antenna. Because you're not really doing far field. I saw some horn antennas back there. Those are most effective and efficient, at least in large, at a further distance, right? But this is a case where you're trying to put something right directly against the human body. It has a different dielectric constant. You're trying to get focusing. So they came up with this design, which, if you guys are familiar with like optics, like lenses, right? What if lenses can focus or disperse? So in lower frequency, you also use dielectric lens antennas. You can do the same thing to focus lower frequency EM waves. What they did was, well, instead of having a 3D curved structure, what if you just flatten it? You use concentric rings, and you change the phase shifts across those rings. You can also get focusing. So that's kind of where this research had gone. And it's nice because then, you know, you can put something like this on top of the human body, transfer power in. However, the question, this is where I came in, was, well, if you're putting like a PCB on someone's body, it's not something they're going to wear for a long period of time, right? Can we make this more comfortable or durable for skin mounting? So next slide. So you can, whether it's an antenna, a transmission line, or some sort of like inductor, you can take this type of a structure and you can break it down into unit cells. So rectangular unit cells. And then you can do this thing, there's different ways to do stretchable. This is just one way. But you can do this thing where you add curvature to each of those traces. And as you make this curve even more windy, the more like a spring it becomes, right? And then there's all sorts of other interesting things involved here that are not shown. Like, do you just take a piece of metal like that, that's like floss, and put it on someone? No, you need to mount it on like a substrate that's also stretchable. And then wait, how do you bond these two things? So I spent a lot of time doing that part. But if you fast forward, and go next slide, you can come up with something eventually that maybe you only have like 2 or 3 versions of that can be stretchable and does work properly. And so that's the structure that we did. The bottom substrate is like a silicone-like material, like a rubber type material. And then you can stretch it. The thinner that substrate is, the more stretchable. And then all that's being shown here is looking at how the properties of that power transfer for like something that was intended to like emulate the human body, how well that works when you're doing stretching. And so we did this thing where like, we swept like a little implant device that would light up when it received enough power, swept it, and then did a camera on long exposure to show the actual focusing that was happening in the body. So okay, that's project 2. One more project. Go next slide. Okay, so this is the most recent one. I worked on this at like a 20% to 30% rate over the past couple of years. And So Livermore is doing, this is supposed to be a plug for Lockheed, but I'm talking about Livermore work. So Livermore is doing a variety of like different advanced or additive manufacturing techniques that you aren't yet seeing like in commercial systems. One of those is liquid metal jetting. Has anyone heard about that before? Okay, so this is, it's different than some of the other approaches that are out there right now for metal printing. But what it is you take like a bulk piece of metal, not like a powder, not like a metal powder. You take a bulk piece, in this case, like tin, and you stick it in this crucible and you heat it to the melting point. And then afterwards, you basically use like air pressure or gas pressure that's controlled electronically to basically extrude droplets. And however you do that control changes the size of those droplets or the repetition rate, how frequently they're coming out, etc. And then you also have to use because when they come out, there's like an oxide layer that forms on the outside. You also have to like confine it in an inert environment. So you have to fill the environment with, in this case, argon to keep the surface from oxidizing. Otherwise you get these like peanut shapes or lemon shapes, etc. And so this is like, we don't have to go through this video, but it's like a video showing the droplets coming out. Actually, maybe we could try pressing it if there's internet. But it's very slow motion, like it's a slow frame rate. It's happening much, much faster. Much faster than this, but that's the droplets coming out. And what you'll see is, after like a long pause, you'll see that there's like variation in the droplet sizes. So what this is showing here is using a high-speed camera to watch this during the whole time. But that's fine for like someone in the lab who's just gonna like do a couple of droplets, just gonna jet a couple of droplets and then stop. But what if you're like actually gonna build a complete part? That's a lot of video, especially because this is like very fast frame rate, right? Yeah, exactly. And so the question that we got asked was, well, can we do something that's less computationally expensive? Because basically these guys, they don't need all this information. They just want to know droplet size, droplet speed, and then if we can, like droplet temperature. That's all they want to know. Can I get something that's not like, n by n by time volume, just like maybe like 1 or 2 parameters and capture that with time. So next slide. Is it not letting you? But is everyone tracking so far? Okay, so what we ended up doing, and there was like a long process to get here, this is like where it ended, was you can use a antenna as a sensor right next to the droplets. And if you transmit a signal and you look at what comes back as the droplets are passing, you can actually detect the changes that are happening. So the horn antennas are optimized for far field propagation, right? They're like very efficient. But in this case, what I wanted was actually just high sensitivity right next to the aperture of a waveguide, right? Like put something as close as possible, because these droplets are like 1 millimeter or smaller. And so I wanted like as good sensitivity as I could have. And so I just put this waveguide right next to the droplets coming down, and then looked at, and I sent just a single frequency. I think it was like 50 gigahertz. Just that one frequency. So not like your typical VNA where you're doing a frequency. Usually we do a frequency sweep. I just did it in CW mode, and then looked at how that one S11 parameter at 50 gigahertz changed with time. And I also simulated it at some point. And what you see is that as the droplet passes, you're sending a signal out, right? And you're looking at what's coming back. That ratio will change as the droplet's passing by. There's like a lot more, that we could talk about why the shape looks this way, etc. But the idea is, look, if you have a 1 millimeter size, you'll get one waveform. If you have a 2 millimeter size, you would get a different waveform. And if you compare, even if I just grab this value, I would know the difference between the droplet sizes. So that's the simple explanation. The next slide. So that video that I showed earlier, this is like 6 images from it, 6 different droplets. And then this is just one capture. This is what I was capturing on the VNA. But you could see smaller droplets had smaller variations, and then bigger droplets had bigger variations. And so I could see, I ended up, for much more data than what's being shown here, you can see that for a lot of different droplets, the diameter does correlate to, if you just pick this minimum point for each of these, there's a correlation between the variation that you get from S11 and the droplet size. And then similarly for, S11 is not just magnitude, right? It's also phase, someone said phase. So the other thing that we saw was that phase variation would vary with how far away the droplet was from the edge of the waveguide, which if you think about it also kind of makes sense, right? The longer distance corresponds to a larger phase change, for example. So, although in this case it's the inverse. Okay, anyways, so that's the last project, and then I have one more slide. So that's just a snapshot of like 3 somewhat random things that I've worked on in the past. But I do want to say that I think there's a lot more fun things to explore about EM and antennas in general. And I remember when I was a student, like everyone always complained about their EM courses because like Maxwell's equations were like really confusing. But I think there's like this is kind of nerdy, but I really think that like EM is very fun and there's some really cool things you can do with it. And so just to like maybe get you thinking about some of the things that are interesting. The first one is like how we take our products for granted. Like if you think about most like Apple products, for example, they're like entirely encased in metal. How are they also radiating? And so like one hint is like maybe that Apple logo is intentional, right? It's not metal. Or maybe like the laptop area here isn't metal inside, right? There's a rim around it that's not. Maybe that's intentional too. And so that's like one thing that I find very interesting, and that's kind of like practical. But there's other things that are more like researchy. So one is like, can we start doing really different antenna design now that we have more advanced manufacturing methods? And then one more is like a little more out there is, can we do advanced manufacturing with microwaves? People are doing it with light right now. That's the primary way, right? But what if you could use like millimeter wave? Light is limited because if you have a material that's opaque, you can't do curing, right? It's just gonna bounce off. But microwaves and millimeter waves are not. And so are there materials that are opaque like ceramics that you would wanna do some sort of advanced manufacturing with? Maybe you can do that with microwaves or millimeter waves. So those are just some snapshots of things that I find interesting. Hopefully that gets you thinking that antennas are like still exciting. So, yeah.
All right, so do you want to take a 2-minute break?
Yeah, so I can set things up
Okay.
and see it.
40 years in
38 to be exact.
38 years in radio, we'll hear yet another form of radio. All about radio.
Martin, and the field of expertise is electromagnetic compatibility and interference. So what my job is to make sure that things don't interfere like they can. So we can walk up to your device and we'll have a different sound, that'll have a different sound, and even then we'll have a different sound. But that's not what we want to hear. We want to hear KCBS or KGO. But amateur radio, believe it or not, has been around for over a century. Seem far-fetched? Possibly. But I also belong to an antique society. We'll pass this around. And this happened right here in San Jose. This is Charles Doc Harold. So we're talking wavelengths that are much bigger than what you saw in the previous presentations. And how he got this radio station on the air in 1909 was power from the trolley cars here in San Jose. And these are the fancy coils that would be the primary and secondary and fed out to a radio tower. I believe it was on First Street, and it was a memorial that had been there for a number of years. So operating this equipment was quite lethal in its day. So feel free to pass that around and flip through that if you so desire. So, and it sounded raspy, and it just covered all sorts of spectrum because he was using a spark. I mean, a rotary gap that would make noise, and he tried to modulate that so you can imagine what it sounded like. It didn't sound very good. So, fast forward to World War I, we had to silence everything because it could be also considered an act of treason if you operated during that period of time, similar for World War II. And the Navy says, hey, we got rid of those pesky amateurs, you know, we don't really need them around. But they persevered and they said, no, the government thought differently. They still have some benefit to the great American public at large, and it could be a way to advance the radio art, okay? And what helped spur and change things in the 1920s? The vacuum tube. Now, this is a two-digit tube that was probably produced in the 30s and used in radio receivers, okay? And this is a more modern one that you would find, like a 50L6, which is a beam power pentode, or used in your audio circuits. These are both audio tubes, so pass them around and take a look at them. One's an octal bass, and the other one's a special keyed bass. And those are thermionic based devices. So in order for them to work, you had to heat up a filament and use high voltage in order to direct the electrons from the cathode to the anode, and that's how all the magic happened, okay? In the early days, prior to vacuum tubes, what did they use to detect radio signals? They used a metal tube, and it was called a coherer, and it was just filled with random metal filings, so that you would have a nonlinear junction in order to get some rectification, so thereby you could have a voltage generator. Now obviously, to hear signals at these wavelengths, the antennas would have to be physically large. But as we fast forwarded through post-World War II, they decided, okay, amateurs, you can have all the fun 200 meters and down. Now, what that means is 200 meters and the wavelengths got shorter. Then they discovered, hey, wait a minute. Where's the globe? I'll need that as a prop, please. The government thought all we should communicate was just with low frequencies because it was predominantly using a ground wave that would usually travel the surface of the earth, okay? We'll get to the high level stuff in a moment. So mountains and things like that would perturb your ground wave, and it seemed to work better along ocean fronts because ocean's a great conductor. Good reference for the antennas. So as we move forward, the predominant mode before vacuum tubes was that was the magic code for the letter C and Q, which stands for CQ, I'm calling somebody. So red may give you a demonstration, that's how you hear things on HF, before you could start modulating and actually hear the human voice. Attributes about amateur radio. It's mostly a communication medium, but it covers a wide number of frequencies. We're talking low frequencies, just below the AM broadcast band, that's 540 kilohertz to 1700 kilohertz. And then we have a number of series of HF bands that allow us to talk around the world. Now, how does that happen? What's all the mysticism behind that? Unlike what you heard in satellite communications, we're talking with LEOs, those are mostly downlinks, and then geosynchronous fixed. Well, there are other atmospheric layers of ionosphere. They're called the D, E, and F layers. During the daytime, the D is the most prominent, and it has a higher absorption. So certain frequencies go into the, that's it, it's just lost in the noise. That's what helps for AM broadcast. But at night, that other layer disappears, and that's when other things and other magic happens. That's when the lat layer is not as strong and the signals bounce. So in the early 20s, it was like the wild, wild west, like the internet was in its earlier days. Meaning, you say, oh, did you hear Japan last night? Wow, that was really interesting. How did you do that? So the signals were weak, and all you had were very simple receivers and circuits to work with. But as you go up in frequency, the characteristics for communications change. As you go above 30 megahertz, these reflective waves don't mean as much, and they start going through. And they continue all the way up to your SHF frequencies, up around 300 terahertz. And ham radio communications have evolved through the years. It's more than just direct person to person. We have the capability of using your laptop to remotely control the station so you can speak to someone else. If you're, say, your residents, you live in a confines where you can't put up large antennas or you have prohibitions. This allows you to communicate with other people around the world with just a digital device like this. And there are other receivers, and I'll mention that later on, how you can eavesdrop and listen to different points around the world via WebSDR or Kiwi SDR. Those are software-defined radios. So let's cancel that. And other factors about amateur radio is contesting. There's some folks that like to just give out their call sign at a certain location and say, I have this contact, great signal, and then they rack up a number of points. So there's contesting. Another aspect of amateur radio is fox hunting. What is fox hunting? Here, I'll give you a demonstration. Very sophisticated antennas, I might add. A Trader Joe's black beans can and a noodle can. Just get the fitting over at a surplus place, look online, oh, there's my cord-away feed point. What this is allowing me to do, gives me directivity if I want to find that signal. But the beauty is, minimizes my interaction because, well, it may affect this part, but that's where all the magic is happening. And preferably, I want to find a signal that's a larger wavelength because this antenna will be desensitized. Then I can hone in and, there it is. And they have contests for people who like to play fox hunting. And it's called a radio sport. Okay, antennas, you can design and build them or pre-purchase some of them depending upon the frequency range you want to use. And for VHF, UHF, if you want something that's more rugged and something you built yourself, yeah, you can go and purchase one. But Ed Fong of Santa Cruz University hosts a great course on antennas and how to work with amateur radio for the VHF and UHF bands. Excuse me. So, what else do I want to tell you about it? Okay, so even your smartphone can act like a ham radio. Yes, this is a transceiver, it's a transmitter. How do we know? And as not Angela, but Tammy was mentioning with regards to Apple, I'm not sure how many of you remembered, they in their infinite wisdom put the antenna along the side of the enclosure. As soon as you put your hand around it, you detune the antenna. The thing wanted to transmit more because, hey, it's a mismatch. I can't reach the cell tower. And people say, hey, why's my battery life going down? Says, what's the matter with you guys? Didn't you? Well, when they tested it, they put it in a plastic holder simulating the human hand. Well, you got a little bit of moisture in here. What does that do to antennas and your E-fields? Guys in the sewer, well, you gotta make a fix on that antenna. So that's how that came about. All right, so The other thing is, you don't want your hands around antennas, particularly if you're pushing a lot of power or current, because depending upon where the wave is launching on the length of the wire, you could either have a voltage peak or a current peak. Anybody gotten bitten by RF? I have. Now I says, I was working at an EMI test lab. I was wondering, gee, is that wave guide getting hot? Never put your finger on a flange. Ow! I said, it felt like a knife burn, except it was going from the inside out. I said, yeah, there's RF there. That was a 200 watt traveling wave tube amplifier, by the way. Yes, they are inherently noisy. So, you gotta be careful with RF, that's all I'm saying. It does wonderful things, but when you're dealing with high power, and some amateurs will run up to as much as the legal limit of 1500 watts. Now, obviously, sometimes you run into cases where you're running at your residence, single family home, you can work all your neighbors. And that's not what you want to do. Working all your neighbors is like you're coming through their telephones, their television sets, their hi-fi, and there used to be a bigger problem, especially with VHF channel 2, because there's an amateur allocation right next to it at 50 megahertz, the original channel 1. So what people would happen is, oh, there's a big contest, I gotta get on there, and people's screens go during the big game. I'm like, where is that guy? I want a piece of him. And I can speak from experience. During my collegiate days at WRSU-FM at Rutgers State University, I was the disc jockey, and you have to hear the air monitor, what's going over the air, not just what's out of the board. And lo and behold, in the student union, 1 or 2 floors above us, I'm listening to my music, and I'm going, that's going out over the air. I want a piece of that person. That's interference. So technically, they should have fixed it, but I wasn't at a Rutgers State University student. I was just some flunky from Middlesex County College, so I didn't really have much to say, but fortunately, that didn't happen too often. So those are cases of electromagnetic interference, and I'm sure every one of you in this room has probably experienced in one form or another. It's just that maybe it doesn't come to you until I probably mention it. That's why I probably not shouldn't using my UHF transmitter, because I could affect their measurements back there in the corner. So you gotta be careful with RF. And speaking of that, get back to my Trenton State days. The college station used to sign on at 10 o'clock in the morning. And one other one other electrical engineer was trying to make a voltage measurement. As soon as we came on, this tiny little 10 millivolt signal went to 50 millivolts. And he says, can't you guys turn it off? Says, we're legal. Sorry, we're at the other end of the building with 1500 watts, but too bad. Build a Faraday cage around it. Well, needless to say, so much for that particular story and that individual. But again, you gotta learn how to live together, co-located as with transmitters. Okay, I'm losing my spot here. Okay, let's move on to the last part. How do I get a license? There are a number of ways via online. The American Radio Relay League has a great program that for you to get familiar with all the technical aspects in terms of knowing the rules and regulations and how to get licensed. And there are regional groups that will perform the test and issue, then you submit it electronically and you get a certificate in the mail or electronically saying you got an assigned call, and it says you are now this leased call. So my original call sign was KB6GSA in 1984, just right after the Olympics. So I missed out on that. But the beauty of amateur radio is that you can also provide communications during emergencies and other situations. You have an additional resource for you to reach out and contact people, which can come in handy. A coworker of mine said while he was not working for Lockheed at the time, he was in Puerto Rico, and he was able to reach somebody stateside because there was no power, nothing. He had to hook up his radio to the car battery and was able to get a contact on 10 meters. 10 meters is roughly 28 megahertz, that's the allocation. But that's the only privileges he had, okay? So when you try to get your license, it comes in 3 flavors. You have the novice class, a general class, and the extra. The novice will get you some of the entry-level stuff, not a lot, but just enough to whet your appetite in terms of, if you really want to operate high frequencies between 3 and 30 megahertz, you have to go up for the general class license. Okay. You want all the HF spectrum, then you get the extra. However, you can still have plenty of fun at the other two classifications. Meaning, I'm an advanced class. My class doesn't even exist anymore. So they've changed the structuring, and it's just like, you can study it, if you can memorize 650 questions, you should be able to, get a passing rate of 80% or better, 10 questions, they'll say, congratulations, here you go. So, some of the fun things I've had through amateur radio throughout the years is operating remote stations and hearing unusual contacts, especially, for instance, when you have what they call a sporadic E, where you're able to bounce a signal and it's not always reliable. There's even some guys that even will bounce their signals off of meteor showers. It only lasts for a brief period in time. And they're able to do communications, just so that they can have that random contact. And as the different layers change, obviously you can predict where your signals are going to go, where they depend upon the A and K index in terms of the solar flares. So, and sometimes you may be taking the short path, but if you're listening to a signal, say from Russia, at a certain time of day, and we're in North America, there's the possibility it'll take the polar path. And that way, it sounds real watery because it's going through that solar vortex. If you think about the various ionospheric layers around the Earth, they're constantly moving. So imagine if you're trying to bounce a signal off of something that's constantly moving, and it also follows the sun. For instance, your higher frequencies, for like say 28 megahertz, is better when you have direct sunlight in the majority of the path of the station you want to work. So right now, we're starting with solar cycle number 25. So if we're in San Jose, we have a tendency, because of the solar path and everything, work stations down this way into Florida and South America. Harder to go in this direction because we're following the gray line of the sun. And it's not necessarily this way, but it's at an angle. So HF can be interesting, but it can also be very frustrating, because you're throwing out your signal out there, who's going to hear me and who's going to respond. But you can also design your antennas to have them close to the ground, or what they call near vertical incidence, meaning you're not trying to shoot for a low angle so you have to minimize the hop to your destination. You're using almost radiating the signal straight up, whereby you have reliable communications within 200 miles. And it's always going to be there because you're not relying so much on the ionospheric layers to relay or bounce the signals. In some cases, it takes multiple trips for you to reach your destination. Say, for instance, if you're calling from North America and want to reach India, it's either polar path, that's going to be pretty long. So the best path is take the shortest path, and that's through the polar vortex. Any questions with regards to amateur radio? It can be interesting, and you can say, oh God, put me to sleep, Jeff. Any questions? Yes, sir.
What are the costs, like the fees for taking the exam to be licensed?
Pardon?
What are the fees associated with the test?
That's the beauty. There are no fees, and thank you for the verbal cue. I also go to electronics flea markets, and there was a ham radio club that were selling their electronics, and some young fellows walked up to him and says, "Oh, look at this cool old stuff, you know, and oh, what are you guys? Oh, we're a radio club. Oh, really? Hey, that sounds pretty cool. How do you get to use one of these devices?" Well, you have to get a license and everything else like that, and then you can join us. Great. Is there a monthly fee? That's how conditioned some people are like, gee, in order to operate a radio, does it involve a recurring fee? No, it doesn't. Back in the 1980s and 90s when I first got licensed, I could place an order for pizza through my ham radio. It's half duplex. I would have to call up to the repeater site. There'd be a remote dialer. Okay, I want a pepperoni pizza to go, thank you. Or health and welfare status, but again, cell phone technology robbed us of some of that magic, but that's okay. It was to the greater benefit of the general public. So, and what I have right here is just to give you a demonstration, because the biggest change for electronics was the transistor. This is a 8 transistor radio. There's 8 active devices in there. This has a lot more active devices than that. This has even more. I even brought one, but it's a kid's toy, and it only has 2 active devices in it. It's barely a radio. But this,
2 minutes away from the KCBS sports line, the Warriors say
the loop
they need to
antenna
be more physical.
is embedded in the lid. So as I rotate it, my line of access, roughly that direction is KCBS, and this is vacuum tube technology. Meaning you have to have a hefty power supply, and this was expensive to operate. Transistors consumed a lot less energy, were far more efficient. You had to have 2 batteries. One was for the filaments, that's your A battery, and your B battery, that was for the rest of the circuitry, for your plate circuits, in order for the tubes to work. This radio would come on instantly because it has, the filament and the cathode are the same. You don't have an isolated element to heat, because you don't want to waste all that energy in just in heat, because you want to maximize your entertainment value for a battery operated device. And the dial face here is going to be confusing to most people, because everything here is listed in Europe in the prior to the 1970s was all listed in wavelength. So if you wanted to find your favorite station here in the United States with this radio, it took a little bit of a challenge. Okay, 200 meters roughly translates to 1500 kilohertz. And conversely, and how do you get to that? Take 300 over the F in megahertz, and that's how you get the properties of wavelength to frequency. So that's how that works. So a number of the things I mentioned today are pretty straightforward and a little tad simplistic, I'm sorry to say, but there are far more things that you can do with amateur radio that it can be done today than when I was introduced to amateur radio. And these were the in things. Slightly bigger than this, but that's all I have for right now. Are there any other questions before we have a part of the demo? Yes, sir.
What are the chances the FCC will get mad at you if you transmitted the wrong part of the spectrum?
I'm glad you asked that question. For the longest time, they had lot more enforcement. But what happened is, for the amateurs, they're self-policing, believe it or not. And believe me, they get hard on people if you're operating in the wrong mode, even the wrong part of a sub-band. So that can become a challenge sometimes for repeat offenders that use foul language, interrupt existing communications for nets that exchange information, and they come hard after them. And if it gets to the feds and you have to build a solid case, that could be a $10,000 fine and forfeiture. So they give you a chance to respond. And since you asked that question, that was one of the reasons why I put this thing together. I wanted to find a guy that was saying something very offensive that I cannot repeat in public on our club repeater. So trying to find him on 30 or 40 miles away is not a problem. What happens when you get too close? I can't make any sense of determination. So let's use a little bit of ingenuity. Hey, for these transceivers, you've got to have to be 60 dB down. That's 1,000,000 times less signal. Hey, now if I get close, I can sort of pinpoint that offending individual. It makes it that much easier. And another thing I want to point out with amateur radio communications on HF, all of the bands are harmonically related. That was not by accident. So that you would not interfere with another licensed service, because in the early days of home brewing equipment, you weren't suppressing your signals. You just wanted to tune it up so you can get your plates to go around and get that contact. In the meantime, it was operating on linear. You're throwing out all sorts of stuff on other bands. And sometimes you can play some other hands like, fix that thing. You're interfering on another conversation on a DX expedition on a remote island. Stop that. And they will direction find you. Well, this is usually for higher frequencies. I was trying to capture somebody on UHF, so I needed to double that, so it was like 855 megahertz. Unfortunately, with regards to that story, I got a visit from the Mountain View Police Department. Excuse me, sir, what are you doing? I'm trying to, here, and I played him the message. He said, oh, well, we got a call from one of the neighbors here. I said, yeah, I understand. You're sitting there and you're looking around and you've got this. So needless to say, Mr. Day, can we see your information? I said, certainly. Not a problem. Hand it off to him. And they handed it back and says, yeah, I served in Iraq, and boy, we could have used a guy like you. So, you know, to explain things and what I was trying to do and so forth. They said, that's really fascinating. This is the best call of our day.
Oh no.
So, that's some of the war stories of trying to find those that are misbehaving, and thank you very much for that question. Any other questions this afternoon with regards to amateur radio and other fun things that you can do with it? Well, does somebody want to hear some noise and static? Because HF can be very interesting, and especially during the wintertime months, it's preferable because you don't have as much atmospheric disturbances. What I mean by atmospheric disturbances? Lightning. It's hard to talk to somebody when you hear a constant. You can put on some other filters, this, that, and everything that makes them even less intelligible. So HF has its own challenges. VHF sounds like a telephone. Some people say, who cares about those telephone bands? Well, they can do certain things too. They can allow you to communicate with satellites like we were talking about. And there's even cases, and the dean of the electrical department at Trenton State College, New Jersey, I wasn't at the time, was very big on EME. What is EME? Earth, Moon, Earth. You're taking a whole lot of signal, usually in the VHF or UHF frequency spectrum, blasting it to the moon and using that as a reflector and then having the signal come back. You're basically watching the noise level go up and down for intelligible information. So those are some of the things that you can do. Now, obviously you need real estate and a little bit of power, but hey, you're college students. You got to think of things a little more innovative. Hey, well, we play with web-based SDRs or remote hams that will allow you to operate a station remotely and talk with other people around the world because, hey, if you're in an apartment complex, look, how many wall warts do you have in your house charging your devices? You think all of those devices add up and contribute noise. Best thing I had when a power outage happened during a heat wave, I could hear all these weak radio stations I couldn't hear before. And as soon as I knew the power's back on, I couldn't hear any of those weak signals. And in closing, my first experience with electromagnetic interference was when I was 12 years old, living in central New Jersey. And I wanted to hear top 40 radio station WYBG out of Philadelphia. That was over 60 miles away, but I kept hearing this god-awful buzz. So bring up the twisted trans. Is it here? Ah, there it is. Mom, see that? That's a light dimmer. See, it's barely on. Doom. Noise goes away. Turn it off. Okay. 2 or 3 days later. Just went downstairs. Boom. Silicon-controlled rectifiers work wonders for dimming lights. The utility companies hated them because they're sending you a nice pure sine wave and you're sending them back junk with all these transients because you're just changing the duty cycle of 360 cycles for illuminating incandescent lamps. So doing so, now you have transients. The reason why AM fell out of favor, it's too noisy. It sounds horrible. It doesn't have to. But with the phalanx of different devices, you can get that, you can stream it, you can do this, and like, so it's falling out of favor, but I do have older radios that date from 1953 to roughly 1964. They would have two markings on the AM radio dial. Why? To avoid radio detection for bombs. That's how sophisticated they were. That's how they honed in on World War I. KGU out of Honolulu, Hawaii, was playing Sunrise Serenade by Glenn Miller, and then the Japanese planes were honing in on the radio station that knew how to triangulate, and that's how they found it. So with those two marks on the radio, whenever there was a disaster, you had to hide underneath the tables and do all this sort of stuff. All the stations would go off the air and they only be heard emergency information on two frequencies. And you tune to those two marks on your AM radio dial, because FM was as popular back then, 60 plus years ago. So that's how they would disseminate information in the event of an early bomb attack in the early 60s. So that was the height of the Cold War era too, mind you. So, and let's see if I can pull this up. Close with this. My dad got me started very early. This young rascal is the one that's listening to one of those two transistor devices. So that was my iPod of the era, so I could listen to the Big 610 KFRC or 1590 KLIV if you lived here in town. I lived in Long Beach at the time, so I like Boss Radio 93 KHJ. Thank you very much for your time. And yes, do you have another question, sir? Okay, appreciate it. Thank you very much. Have a great day now.